Hello, my name is Kevin Cavell and I'm the product manager for the new Agilent source measure units. These new SMUs are modules that are part of the N6700 modular power system family. For this demonstration, the SMU will be installed in this N6785B DC power analyzer mainframe. Now let's take a look at the new Agilent patented feature we call seamless measurement ranging. Today's test setup consists of a demo board connected to the new N6781A 2-quadrant SMU for battery drain analysis. This demo board will simulate the dynamic current that is typical of a battery-powered device as it transitions between states of operation. This type of dynamic power management is used in many battery-powered devices such as mobile phones, e-book readers, and medical devices where power consumption is critical. To control the SMU and analyze the data, I'll be using the new 14585A control and analysis software for the DC power analyzer. The software is not necessary to use the DC power analyzer, but it does provide usability enhancements. Right now, the SMU's built-in 200 kHz digitizer is capturing the dynamic current being sourced to the demo board. We can see the current pulses here in the scope view mode of the software. Let's zoom in on one of the pulses so we can see it better. I'll change the time base from 200 milliseconds per division to 5 milliseconds per division so we can see the pulse better. These pulses vary between 125 microamps and 120 milliamps. This is a 1,000 to 1 change in current, which is difficult to measure. Traditionally, in order to measure a dynamic current such as this, you would have to choose a measurement range that can capture the higher 120 milliamp portion of the pulse. In our case, the 3 amp measurement range is the correct range. Let's use the markers to measure the 120 milliamp portion of the pulse. So we'll turn the measurement markers on. We'll drag the markers over to the pulse. And we can measure the average current of approximately 120 milliamps. If we move the markers over to the lower portion of the pulse, we can see that the average current is bouncing all over the place. This is because we cannot make an accurate measurement due to the offset error of the 3 amp range. Thus, in order to capture the entire waveform, you sacrifice the low-level accuracy needed to measure the 125 microamp portion of the pulse. Let's zoom in on this portion of the pulse to take a closer look. I'll change the amps per division from 50 milliamps to 1 milliamp per division. Now we can see the measurement noise more clearly. Let's switch the measurement range to auto to show you what you get when you use seamless measurement ranging. As soon as we turn on auto, you can see that the measurement noise disappears. This is because the measurement range is automatically changed to 1 milliamp and we are now capturing the 125 microamp portion of the pulse accurately. You can see the average measurement is approximately 125 microamps. If we zoom back out to see the whole waveform by changing from 1 milliamp per division back to 50 milliamps per division, you can still see we are accurately measuring the 125 microamp, and if I move the markers over, we're still accurately measuring the 120 milliamp portion of the pulse without overloading the measurement system. This concludes the demonstration of how Agilent's new SMU modules provide insights into power consumption by enabling engineers to see the complete current waveform they've never seen before, from nanoamps to amps, in one pass and one picture. Thanks for watching.